In this video, we're going to talk about infinite limits, and the way we create an infinite limit is by having a vertical asymptote. A vertical asymptote is when the function is going to get bigger forever or smaller forever and never stop. It occurs when we see in a function that we have direct substitution. It results in a number in the numerator and a 0 in the denominator. So 0 over 0 is indeterminate. However, if we end up with a number over 0, that does tell us something. So when we're saying that a limit equals infinity, we're saying it doesn't exist. So we're still saying that it doesn't exist because infinity is not like a real number that exists. But infinity does describe the end behavior. So it kind of goes one step further to say why it doesn't exist, because it approaches infinity, because it goes up forever and ever and ever. So here are some examples. If we were to find the limit, in this case, as x approaches 1 of this function, we would say does not exist. Because as we come in from the left, we go to negative infinity. As we come in from the right, we go to positive infinity. If we look at example B, and we look at the limit as x approaches 1 of f of x, here we could say infinity, because from the left and from the right, they're both going up. So this says that limit doesn't exist because it gets bigger and bigger forever. Back here, we can't pick negative infinity or positive infinity, so that's why we still have to say does not exist. However, if we do change the problem to say maybe only from the right, now we can come in only from the right, and we see that it does get bigger and bigger forever. So in this case, we would say positive infinity. And again, we're still saying that it doesn't exist, but we're stating why. We're saying because it gets bigger forever and ever. So in order to find the vertical asymptotes, we need to figure out when we see the situation where we have a number divided by 0. So in this case, we have a number on the top. We want to know when when the denominator equals 0. So in this case, if we simplify, we see that x equals negative 1. So since that produces a 0 in the the bottom, but not in the top, this is a vertical asymptote. So we would say there's a vertical asymptote at x equals negative 1. If we look at example 2, there's actually 2 places where the denominator equals 0, but not all of them are vertical asymptotes. We must make sure we get a number in the top. So the best way to look at this is to factor both the numerator and denominator. So when we factor the numerator, we know that positive 4 and minus 2 multiplies to negative 8, but also adds to positive 2. And in the denominator, we have that difference of perfect squares. So we'll have x plus 2, x minus 2. So there are 2 places of discontinuity. We have negative 2 and positive 2. However, since that one cancels, that means this factor does not produce a vertical asymptote. So my only vertical asymptote then is going to be when my new function has a 0 in the denominator, which is at negative 2. So here I'll say a vertical asymptote at x equals negative 2. And that's because when I plug in negative 2 in the numerator, I get 2. In the denominator, I get 0. And that indicates a vertical asymptote. Positive 2 doesn't indicate a vertical asymptote because if I plugged in positive 2 here and here, I would get 0 over 0, which is indeterminate. So here's some properties of infinite limits. If we say that C and L are real numbers, and let's say the limit of f is infinity and the limit of g is a number, if we take infinity and add it or subtract it to a number, it's still super big. If we were to multiply them, infinity times a number is still huge. If, let's say, the limit is negative, infinity times a negative goes to negative infinity. And we'll talk about this one later. So we have 2 examples here. We're going to find the limits. The limit of a constant is just a constant. So that guy stays 1. When we plug 0 in here, we get 1 over 0, which means there's a vertical asymptote. So a vertical asymptote at 0 means the function either has to get really big or really small. So we need to see what happens as we get close to that vertical asymptote. It could go up, it could go down. We need to see as I come in on the left and the right to 0 what happens. So the easiest way is to make a table. And since we're approaching 0, we'll have 0 in the center. And we'll get close to 0 from the right and from the left. So if I plug -2 into this function, I'm going to get 1 over 4. And if I plug -1, I'll get 1 over 1. So as I'm approaching 0 from the left-hand side, it's getting bigger. It's approaching infinity. If I plug in 1 to my function, I get 1. And right now, I'm just plugging it into this function here because we're going to add it to 1. When I plug in 2, I'll get 1/4. So again, as I get closer and closer to 0, my numbers are getting bigger, which means this function's approaching infinity. So this limit is approaching infinity, and 1 plus infinity is infinity. If we look at our final example here, here we're approaching only from the right. So if we have to make a table, we don't have to check from the left and the right. We just have to check from the right. So when we plug this in, we do get 2 in the numerator, and we get 0 in the bottom, which means there is a vertical asymptote. So I know the limit is either infinity or negative infinity, but I need to figure out which one. So in my table here, I'm approaching 2 from the right, so that's going to be bigger numbers. So I'll do maybe like 4, 3, 2. I'm approaching 2 from the right. And I'm just plugging these into my function. So here I'll have 4 over 2. When I plug in 3, I'll have 3 over 1. So as I'm approaching 2, again, my numbers are getting bigger. Since it's a vertical asymptote, if I start to get bigger as I come in on the right, I know I'm approaching infinity.